Hello and welcome to this tutorial on regression using multilayer perceptrons. So first, as an outline, we will start with the introduction, the biological motivation of perceptrons, typical activation functions, and of course multilayer perceptrons. We will then use those multilayer perceptrons to tackle a specific material science regression problem using the so-called LMNet architecture. We will discuss in detail the task and the dataset creation and the typical steps that you have to take in a machine learning project, namely training test split, model definition, training phase, and of course evaluation of the results using typical performance metrics and visualization techniques. And at the end, we will test the model. So what is deep learning? In deep learning, we are dealing with artificial neural networks. They date back to, and the most simple version of them is the perceptron. These models date back to the early 1940s and 50s. And the motivation comes from biology in the following way, namely that we have this very simple model of a biological neuron with input virus, the dendrites, the output, the axon, and the cell body, which in a perceptron is modeled by input values x1, x2, real numbers, which are combined in a linear combination with weights w1, w2. This b is also called the bias value. And then an activation function f is applied to calculate the output y. And one can use that in case of binary classification, for example, together with a so-called heaviside activation function, which will simply return 1 if the argument is greater than 0 or 0 otherwise. So it will basically determine when the neuron will fire or not. Other activation functions that one can use are, for example, sigmoid or tangent symbolicus, but we will also see another one. And we can extend this simple model to multi-layer perceptrons, where you now have several neurons here, which is now called a hidden layer. You have input, 6 neurons, output, 4 neurons. In this case, just an example could be 4 different classes represented by these vectors. And the first step is now when you want to calculate the output in so-called forward propagation. And the first step is to calculate the linear combination here, as before for the perceptron, but now with more weights w, which are collected in this vector. And then the linear combination is expressed via this dot product. Similarly, you proceed with different weights w prime for the second activation value, and so on. And then you can summarize that in vector matrix notation like this, and with a weight matrix w and the vector of activations a. And finally, to calculate the output y, you do the same thing as before. You have a different weight matrix w prime and different activation function f prime. So this would be a very shallow network, only one hidden layer. A deep neural network would be something which has at least 2 hidden layers. Okay, so the main feature of neural networks now is really that they can learn their own representations, possibly complex representations. And one example is in particular image classification, where they really have produced state-of-the-art results, where, for example, here a pixel input is mapped to a specific object identity. So is this a person, is this a car, or is it an animal, the specific image? And the features that are extracted get more abstract from layer to layer. So you can see, for example, here the first edges and then more abstract parts of the object in the image. And the main reasons for the success of deep learning, although it is very well known since 1940s, 50s, the basic models and then later also the perceptrons, is that we have now much more training data, with, for example, being ImageNet database, and also in particular more computational power with GPUs. And this allows us to train much larger neural networks, which then really, as it is sketched here, outperform other machine learning algorithms while at the same time avoiding overfitting. And of course, there are advances in algorithms, namely the backpropagation algorithm, which allows you to calculate the gradient for the training phase in a computational efficient way. Also new regularization techniques, for example, dropout, you will see that in the tutorial, and new activation functions such as the rectified linear unit or short value, which basically simply cuts off the negative part for a given input x. Okay, and when you will see in the tutorial, we will implement deep neural networks using the so-called Keras Python library, and it is quite simple to understand. Then you first import here, and then you define the input which is here 10 input neurons, specific name, and then you can simply add as many layers as you want. So dense means that it's fully connected, or multi-layer perceptron. You have 128 neurons, specific activation function, which is here the ReLU, very commonly used. And then we also have this dropout regularization, which you will see in the tutorial in more detail. And at the end, an output. Here we have, unlike before, we had 4 output neurons. Now we have 1 because we want to do regression in the tutorial. So one number as output. And then we compile the model and fit it to some training data while also validating it at the same time on this validation set and training it for a specific number of epochs. What that means, please refer to the tutorial. So what we will do in detail is that we predict a specific physical property of inorganic compounds, namely the volume per atom, and the data comes from the OQMD, the Open Quantum Materials Database. And the architecture we use, as I said at the beginning, is called LMNet from this publication here, and then we can predict this target property. So thank you very much for your attention. You can contact me during the tutorial or via mail.